Now we'll look at Dijkstra's algorithm for finding shortest paths in graphs with non-negative edge weights. Dijkstra is a famous figure in computer science, and you can amuse yourself by reading some of the things that he wrote. He was a very prolific writer and kept notebooks, and here are really some of his famous quotes. Now you need to maybe know something about old languages to appreciate some of these. For example, COBOL was one of the first business-oriented languages, programming languages, and it tried to make it so that programs kind of read like English language sentences. But purists in computer science, such as Dijkstra, really didn't like that language, as you can tell. The use of COBOL cripples the mind. Its teaching should therefore be regarded as a criminal offense. Actually, when I first came to Princeton, was setting up the department here. There was a big donor who actually wanted to have me fired and the department closed down because we wouldn't teach COBOL. I didn't know about Dijkstra's quote at that time. I wish I had. And there's some other opinions that Dijkstra had. You can amuse yourself on the web reading some of his writings. But he was, here's another one that's actually pretty relevant today. Object-oriented programming is an exceptionally bad idea which only could have originated in California. Dijkstra worked in Texas, University of Texas for a while, and of course came from the Netherlands. But Dijkstra did invent a very, very important algorithm that's very widely used for solving the shortest paths problem. It's the one that's in your Maps app and in your car and many, many other applications. So let's take a look at how that algorithm works. It's a very simple algorithm. We consider, what we're going to do is consider the vertices in increasing order of their distance from the source. So in the way we're going to do that is take the next vertex, add it to the tree, and relax all the edges that point from that vertex. So let's talk about it in terms of a demo, and then we'll look at the code. So our mandate is to consider vertices in increasing order of distance from the source. Our source is 0 in this case. What vertices are closest to the source? We can look at the edges that point from that vertex. Let's start out with vertex is 0 is at distance 0 from the source, so we pick it. Then we add that vertex to the shortest path tree and relax all its edges. And relaxing all the edges pointing from 0 in this case is just going to update the dis2 and edge2 entries for 5, 8, and 9. So in this case, this says that the shortest path from 0 to 1 is to go along 0, 1, and that's distance 5. And from 0 to 4, it's to go along 0, 4, and that's distance 9, and 0 to 7, let's go take 0, 7, that's distance 8. And the edge weights are positive. We're not going to find a shorter path to any one of the edge weights are positive, and those are the shortest paths that we know so far to those vertices. Now the first key point of the algorithm is take the closest one. If you take the closest one, in this case it's 1, then we know we're not going to find a shorter path to 1. The only other way to go out of 0 is to take one of these other edges, and they're longer. And all the edge weights are positive, so we're not going to find a shorter way from 0 to 1 than to take the edge 0, 1. So that means that edge 0, 1's on the shortest path tree. That's what the algorithm says. Take the next closest vertex to the source. In this case, it's 1. And then we're going to add that vertex to the tree and relax all the edges that point from that. So now both 0 and 1 are on the tree, so now let's look at the edges pointing to that. And we have to relax each one of those. So in this case, if you go from 1 to 4, then we look at 4, we know a path of length 9, and 1 to 4 doesn't give us a shorter path, so we leave that edge alone. 1 to 3 gives us a shorter path to 3, which is going to be 20, because you went from 0 to 1, and then 1 to 3 is of length 20. And 1 to 2, also we didn't know a way to 2, but now we know one, or a better one, is 17. So that completes the relaxation of all the edges pointing from 1. So now we have 0 and 1 on the tree, and we consider next the next closest vertex to the source. So what we have in DIS2 is the shortest path to all the vertices that we've seen so far, and this one says that and we've been to 0 and 1, so the next closest one is 7, which is distance 8. So we're going to choose vertex 7. And again, that's the shortest path we've seen so far. We're not going to find a shorter one, because to get to every other vertex is longer. And so we know it's on the shortest path tree. And now we're going to relax all the edges pointing from 7. In this case, both of them, the one from 7 to 2 gives us a shorter way to 2 than what we knew before. And the one from 7 to 5 gives us a shorter way to 5 than we knew before. Well, we hadn't been to 5 before. So that relaxes 7. So now 7's on the shortest path tree. So now 4 is the next closest path vertex to the source from the edge 0, 4, which is of length 9. So that's the one that we're going to pick next for the tree. We're not going to find a shorter path there. And we relax along all its edges. In this case, we find a shorter path to 5 than we knew before, and a shorter path to 6. Well, we visit 6 for the first time. Okay, so that's 4. So now we just have to worry about 2, 3, 5, and 6, and 5 is the winner there. So we select vertex 5, relax along its edges. In this case, those edges both give us better paths than we knew before. So now we're left with 3 vertices, and 2 is the winner. This is the 2 from the source is 14. To 3 it's 20, and to 6 it's 26. We relax its edges, and it gives us, again, new shorter paths to both 3 and 6. And then the next to last step is to pick 3, and that does not give us a new way to 6. And then finally we pick 6. And then we now know the shortest paths to all the vertices from vertex 0. If we just take the edge 2 edges, that's from to 1 you take 0, to 5 you take 2, and so forth. You get the shortest paths tree, and that gives the shortest way to get from the source to every vertex. That's a simulation of Dijkstra's algorithm. Here's a demo of Dijkstra's algorithm running on a large digraph. So the source is the vertex in the center with the open circle, and you can see it considers the vertices in the graph in order of their distance from the source. Now you can see this is maybe like a lake in the middle of the graph, and so it's not going to move on from those vertices. It's going to take a little while to get around the lake. And again, if this visualization is produced by our code, and it gives a very natural feeling for the way that the algorithm works. This, in principle, and I think in fact, in many cases, is what your car does when you turn the map system on. It computes the shortest path to everywhere, and then it's all ready when you ask for a certain place, how to get there. So here's just starting from another point in the graph. If you happen to live at a corner of the Earth, then it's going to be slightly longer to get to the other corner. And a nice feeling for how the algorithm gets its job done. Again, when it gets into those blank areas, it takes a little while to get it over to the other side. And of course, if we had islands, if we had little roads in the middle there that were not connected, there'd be no way to get to them from the source, and we wouldn't see them. And that's fine for the way our algorithm works. We just leave that out of the demo and the proofs to avoid adding an extra comment about that for every algorithm. So that's a visualization of Dijkstra's algorithm on a large graph. So how do we prove it's correct? Well, essentially, we prove that it's an instance of the generic algorithm. So first thing is that every edge is relaxed exactly once. Every time we put a vertex onto the tree, we relax all the edges that come from that vertex, and we never reconsider the vertex. And what does relaxation do? Relaxation ensures that after the relaxation, either way that it was before, afterwards you have the distance to w is less than or equal to the distance to v plus plus the weight of the edge. Either it's equal because we just made it that way, or it's less because it was before and the edge is not relevant. This inequality is going to hold for every entry, for every edge corresponding to every edge, for dist2 entries corresponding to every edge, because number one, the dist2 values are always increasing. Are always decreasing. The only thing we ever only reason we ever change dist2w is to make it smaller. If we found an edge that would make it bigger, we ignore that edge. So it's always decreasing. So when we change dist2w, we're not going to make that inequality false. We're just going to make it better. And dist2v is not going to change at all. Once we relax an edge from a vertex, we're done with that vertex. We're not going to process it at all. So then when we're done, we have the optimality conditions hold. That exactly is the optimality condition. And not only that, we have a path from the source to every vertex. So that's a correctness proof for Dijkstra's algorithm based on the optimality conditions. Here's the code. It's similar to code that we've seen before. We're going to use the indexed priority queue that allows us to implement the decrease key operation. And we have our edge2 and dist2 arrays that are part of the shortest paths computation and the goal of the shortest paths computation. We initialize, the constructor initializes those arrays, including the index minimum PQ. And we start out with all the distances infinity, except for the distance to the source is 0. We put the source on the priority queue, and then what we're going to do is take the edge that's closest to the source off the priority, that's on the priority queue, off, and then relax all the edges that are adjacent to that. So I'm using our standard iterator to get all the edges that emanate from that vertex and relax them. And then the relax code is just like the code that we showed when describing relaxation, except that it also updates the priority queue. If the vertex that edge goes to is on the priority queue, it gives a new shorter way to get to that, so we have to decrease the key on the priority queue. If it's not on the priority queue, we insert it. And that's it. That's a complete implementation of Dijkstra's algorithm using modern data structures. Now, this algorithm might seem very familiar if you've been paying attention. It's essentially the same algorithm as Prim's algorithm. The difference is that in both cases, we're building what's called a spanning tree of the graph. But in Prim's algorithm, we take a vertex that's not on the tree using the rule of let's take the vertex that's closest to the tree, anywhere on the tree closest to some vertex on the tree. For Dijkstra's algorithm, we take next the vertex that's closest to the source through a path that goes through the tree and then into a non-tree vertex. That's the difference. And the differences in the code have to do with the fact that Prim's algorithm is for an undirected graph, Dijkstra's algorithm is for a directed graph, but essentially they're the same algorithm. And actually, several of the algorithms that we've talked about are in this same family. They compute a spanning tree. You have a tree that takes care of that records where you've been in the graph from every vertex back to where you started. And they use different rules for choosing which vertex to add next. For breadth first search, you use a queue. For depth first search, you use something like a stack, and then you have to decide what to do if you encounter a vertex you've been to before. But many graph algorithms use this same basic idea. So in particular, when we're talking about what the running time of Dijkstra's algorithm, it depends on what priority queue implementation we use. And it's the same considerations as for Prim's algorithm. We have V insert operations. Every vertex goes onto the priority queue. V delete min, every vertex comes off the priority queue. And for every edge, in the worst case, we could compute a decrease key operation. So the original implementations of Dijkstra's algorithm used an unordered array, which would mean that it would take time proportional to V to find the minimum, to find the vertex closest to the source. So the total running time would be proportional to V squared. That's not adequate for the huge sparse graphs that we see in practice today, like the map in your car. So the binary heap data structure makes it feasible to run this algorithm, and that's where all the operations take time proportional to log V. We have to use the indexing trick that we talked about last time to support decrease key, but still we get a total running time of E log V, which makes it feasible. And just as with Prim's algorithm, by using a implementation of the priority queue that can do a faster decrease key, you can get a faster algorithm. And in practice, something like a four-way heap is going to give quite a fast algorithm. That's a little more expensive to insert, but much faster to delete min and decrease key. And again, there's a theoretical data structure that's not useful in practice that gets the running time down to E plus V log V. Of course, if your graph is dense, and again, the examples I use, they're not, the array implementation is optimal. You can't do any better. You have to go through all the edges. You might as well find the minimum at the same time. But in practice, people use binary heaps for sparse graphs, maybe going to four-way if the performance is really critical. The bottom line is we have extremely efficient implementations for the huge graphs that arise in practice nowadays.